Yeah, we're ready and recording.
Okay, perfect. Well, welcome everyone. Thank you so much for coming. Uh, First of all, before I get started, like Zoom is a really weird and awkward place and there's latency and stuff. If you have questions or comments or anything, feel free just to interrupt me. I would prefer to feel like we're having a conversation than that I'm just like talking out into the void. So I promise I won't be offended. So I want to talk about this database that I've been working on. It's called unifyDB. I'm calling it a time traveling graph database, which is sort of just a fancy way of saying that it persists the complete history of everything you put in it. You know, you'll never overwrite data, you'll only append data. You'll notice that I just have a screenshot of the GitHub repo here because this project has no logo and it's a database, so there's no UI. So this was the best I could do. But maybe one day it'll have a fancy logo. So here's how things are going to go. I'm going to start by talking about like what the database does. We're going to define some terms just so that the rest of the presentation will make sense. I'm going to talk about how it works at a pretty high level. At some point, you know, if you guys are curious, I'm happy to dig in and show you the code as well, but I just kind of want to start with the high level thing. And then if people are curious, you know, we can dig in as you want to. We're going to talk about the database architecture, both as it exists now and as it like should exist one day when it's done. I'm going to do a little bit of a demo just to like show you guys what I have. And then I've reserved some time to talk about the code base, but I don't really have like a concrete plan here. We can talk about like the library, the Clojure libraries that's powering the thing. We can talk through some of the algorithms and data structures if you want, or we can just go look at interesting bits of Clojure code. I'm kind of going to let the group guide that. And then, you know, we'll have like dedicated Q&A time at the end. But like I said, if you have any questions, feel free just to interrupt me. So unifyDB, what is it? It's a work in progress. I'm going to talk about that a little bit, what's done and what's not. It's a graph database, right? So it's not just storing tables. It likes to think about entities and the relationships between them. And this might sound a little familiar to anyone who knows about Datomic. It stores the complete history of all persisted entities. It has a data log-based deductive query language, which we're going to kind of talk about what that means in a little bit. And it has built-in access control. The guiding principles, like why I built this thing, mostly stem from like a frustration at work that I felt like every new project, I was just implementing the same stuff over and over and over again. Like we always needed an access control system. Eventually, someone always asked me, hey, like, why did this booking change? I work for a travel company, so we do a lot of things with flight bookings. Why did this booking change? Who changed it? And the answer was, I don't know, like the database is different now. And so we had to go and build like, you know, a whole lot of custom audit logic. So I think those things should just be built into the database, right? There's no reason that such a common application requirement should have to be re-implemented over and over again. Queries should be data, not text, right? Like, don't get me wrong, I really like SQL. I think SQL is an amazing query language, but the way that people do SQL in code is like generally terrible, right? If you do string concatenation, you've opened yourself up to a SQL injection. So you have to do things like query parameterization or an ORM, and then you end up with this kind of like abstraction layer and you're never sure exactly what's going to get sent to the database. So queries in unifyDB are just data structures that can be represented in any programming language. That can be Eden, right? The extensible data notation. I think database clients should feel native to your programming language. So if you're writing some code that talks to your database, that code should look and feel like the code that you're writing in the rest of your application. You shouldn't have to paradigm shift. And finally, databases should be easy to run in development, right? You should just be able to run a command and spin it up on your laptop and get going. But they should be scalable for production deployments. You should be able to distribute it. You should be able to have, at the very least, you know, horizontal read scaling, preferably horizontal write scaling, although as we'll see later, unifyDB actually doesn't have that because that's a super hard problem. So those are kind of the things that I kept in mind as I started writing this project. So where am I at? I've been working on this thing about a year and a half, right? Since August of 2019. And it's like very much unfinished. There's a bunch of stuff that it can do and a lot more stuff that it can't do yet. So for the rest of this presentation, I've color coded it. Anything that's written in black, just regular text, that means it's done, it's in there. Blue is partially implemented. Like usually that means that the abstraction is in place, but like the concrete implementations aren't, or sometimes it's just, halfway done. Red, haven't even started it. It's something that the database is going to have one day, but still hasn't been done. All right, let's define some terms. So like I said, unifyDB is a graph database, and specifically it's a type of graph database called a triple store. A triple store refers to, a triple is like a 3-tuple, right? It has a subject, a predicate, and a value. So something like ID1 name Jeremy, that's a triple. So I call those facts. It's kind of like the base unit of knowledge in a database. If you're familiar with Datomic, again, this is what Datomic calls datums. So you can have sets of facts that are either all true, or maybe some of them are true and some of them are false, but they are all in a particular state at a particular time. That's called a transaction. So it's an atomic operation that asserts or retracts a set of facts. And the atomic bit is important here, right? If you have a transaction, like all of those assertions that you make are always going to be true. It's never going to be in some halfway state. And the final important term here is rule. This is kind of borrowed from Datalog. A rule is an operation where you tell the database how to infer new facts from existing ones. But this is pretty interesting. This is something that kind of a lot of mainstream databases don't have, right? We'll talk through what this really means and how it works in a little bit. All right, I'm gonna get into the colorful rainbow of things that I've done and things that I haven't done yet. So what can the database do? It can transact and persist facts. You can put data into it, right? It can execute queries, but this one is in blue because you can't do any aggregation things yet. So in SQL, aggregation is something like a group by or a count or a sum. None of that stuff's implemented yet, but you can ask questions about the data and get answers back. And actually you can ask some fairly sophisticated questions even without the aggregation stuff. We'll talk about that soon. It can infer new facts from existing ones using rules. You can query facts from a past database state. So this is kind of the audit log stuff that I was talking about, right? Like sometimes I don't want to know what my data looks like right now. I want to know what did my database look like when this booking was made 3 weeks ago. So you can ask those kind of questions. Eventually, unifyDB is going to support a schema system where you can say this particular predicate is always going to be a string, right? You can say a name is always a string, and the database is not going to let you persist any facts that have a name value that's not a string. That's not in yet, but the system where you can say that there are schemas about predicates is in. In reality, the only predicates that are currently implemented are cardinality, which means is this predicate referring to many things or one thing, right? So for example, you could have a fact called favorite color. And favorite color is only one. You can only ever have one favorite color. And if you transact a fact that says favorite color red, and then you transact another fact about the same entity that says favorite color blue, that entity's favorite color is only blue. You've overwritten the other one. But you could also maybe have a predicate called favorite foods, and you can have many favorite foods, because why would you want to just choose one? And if it's cardinality many, then if you transact new favorite food facts about the same entity and you query on them, you're going to get back a whole list, all of the things you've ever asserted about that predicate. All right, so that's schemas.
I have a quick question.
Sure.
When you said it overwrites it in the case of the red blue favorite color, are you really doing that, or are you just actually updating the thing and you could, that previously my favorite color was red, but now it's blue.
Great question. It's the second one. So in the database, you're still going to have both facts. You're going to have favorite color red and you're going to have favorite color blue. But one of them is going to have a higher transaction ID than the other one, which is how unifyDB knows which thing has been asserted second. And so in your queries, you're only ever going to get back the most recent one unless you specify that you're looking at the database at an earlier transaction. And I'll have an example of that later.
So do all facts have a transaction ID sequence then, or is it a universal thing?
They all have a transaction ID sequence. I kind of lied when I said it's a triple store, which is the next slide. It's actually a 5 store. There's 2 additional attributes in every fact.
So transaction ID is like a watermark then, right? For you to position yourself to see what's there, what's the latest less than that, basically, right?
Yeah, exactly. And they're sequential, so you always know that. Yeah, and in fact, I realized recently that I should have just made them timestamps, and I'm probably going to change that and just make them timestamps. But right now they're just sequential IDs.
But it's
so you know that,
but you're doing it atomically, so you don't have to use timestamps. Timestamps would be more expensive. So you just have an increasing kind of monotonically increasing number. Yeah, I've done some stuff like this too, so I want to talk to you about that maybe later. But I know where you're
definitely.
at.
All right, so the database has an HTTP interface, which is slightly unusual. I think that actually many databases these days you talk to over HTTP, although a lot of them have, just kind of more custom TCP protocols. This one doesn't. It's like a pretty vanilla HTTP REST server with a query endpoint and a transact endpoint. And it only speaks Eden because Eden is a more sophisticated serialization format than JSON that lets you encode more things. So that's going to be a little complicated when I get to implementing clients, but since I haven't done that yet, who cares, right? All right, so you can query the history of a set of facts. This is mostly done, and we'll see that later. I put it in blue because I don't really love the API I put around it. It's kind of clunky, and I'm probably going to change it. These last 2 things are in red. They're completely not done yet. It's the access control stuff, right? So eventually, I want you to be able to say, this user or users of this type cannot access the credit card predicate. Only admins can access the credit card predicate. And that's just going to be built into the database. And if a non-admin user makes a query that attempts to access the credit card predicate, they just won't get any results back. And finally, the other red thing is native clients for programming languages. There are currently 0 clients, not even a Clojure one. So that's I want to wait until the API is totally nailed down and the core of the database is where I want it. All right, so this is what we're getting ourselves into. Are there any other questions at this point? Cool. All right. So let's talk about facts. So like I said before, a fact isn't actually a triple, it's a 5 tuple. And the 5 components of a fact are the entity ID, which is just a unique identifier that groups facts into entities, right? And entity is just like a thing, like some object that lives in your domain. There's an attribute and a value. Those ones I think are pretty self-explanatory, although it is worth noting that the value can be any Eden object, not just scalars. It's kind of interesting. There's a transaction ID. Now, under the hood, transactions are also just entities that can be queried the same way. So every time you transact a set of facts to the database, we create a new transaction entity. And this is going to let you query those transaction entities and see a history of all of the transactions you made to the database. And finally, there's a Boolean that I called added because I didn't know what to call it. If this Boolean is true, you are asserting this fact. You're saying this is a fact about the world. If this Boolean is false, you are retracting this fact. And you're saying this fact maybe was true at one point, but as of this point in time, it's no longer true. So that's how we handle deletions, because remember, you can never actually mutate any of your data. Once it's in the database, that's it. So
if you want to, sorry. I have a question.
No, go ahead.
Is that okay?
Yeah.
If you want to retract, is it valid to have a fact in the log where you are retracting an entity attribute value triple that was never there? Like, is that a valid state?
Yeah, that's a valid state.
And it just has no particular meaning because.
Yeah, it's like kind of a meaningless state.
Okay.
I'm trying to think if there's any.
Okay.
From the outside, you can't tell the difference. Right. From the outside, you can't tell the difference. If you query for it, it's not there. Either because it's not there or because it's false.
Yeah, but if you were to query the transaction log, you would see a retraction
still see it
with no assertion beforehand. Yeah, that's kind of interesting.
So to actually, so the only way that this is, envisioned or meant to be useful is if the entity attribute value triple matches something that was previously asserted. The transaction ID can be different and the added flag is intentionally different, right?
Yeah, exactly.
Okay. Great, thanks.
Yeah, so this diagram down here is just showing how you would map like kind of a more traditional like hash map data structure like you use in a programming language to this fact model, right? So, you have key value pairs, just a hash map, and then name, then bit diddle, that is just the same fact we were looking at up here. Like I said, facts can be, don't have to be scalar values. So we see that Ben's a computer wizard, and that just ends up as a triple that has a nested list inside of it and its value. This one's kind of interesting, right? You can have nested maps. How would you represent those? Well, actually, this is just a fresh entity. And so we can see that we had ID1 that was assigned to the outer entity. And we have this ID21 that was assigned to the inner entity. And we can see that ID1 has an editor attribute with a value of ID2. So this is supposed to showcase the graph capabilities of unifyDB, where you're asserting relationships between entities. And we index on these back references, so it's really easy to look up, how many people have their editor as Emacs, questions like that. So, transacting. This is the operation by which you put data into the database. So as it exists right now, unifyDB expects slightly different format than the fact format I just told you for its transactions. So you obviously don't know the transaction ID beforehand, right? Because it hasn't been created yet. So instead you give it an operation name. So you're either gonna add or you're gonna retract a fact. And then you give it an entity, an attribute, and a value. But you'll notice these entities are not IDs, because what if you haven't created this entity yet? How do you do that? So this is what's called a temporary ID. It's only valid inside this transaction. And if unifyDB sees a temporary ID in the ID slot of a fact here, then anything with this string in it is going to be replaced by whatever the ID ends up being. So we can see that this first fact is going to create this entity called Ben. And then this third fact here is going to say that Ben is the supervisor of Alyssa. And if we look down here, what that gets translated to is we've given Ben unifyDB ID of 1, and we've given Alyssa unifyDB ID of 2, and we can see that 2's supervisor is 1, right? Is everyone familiar with keyword, namespaced keywords? Okay, so that's what this is, right? Or not namespaced keywords. The
reader literals.
Reader literals, thank you. Tag literals, yeah. So the ID is like a special data type in unifyDB because we need a way to differentiate them from like regular numbers for the purposes of populating the back reference index. So this was my solution to that. An ID is a special data type with a reader literal that unifyDB knows how to understand. A couple of other interesting things about the transactor. There is a magical temporary ID called unifyDB.tx, which is always going to resolve to the ID of the transaction that you're about to create. So you can add metadata to transactions, right? So in this case, we're adding some metadata to this transaction called a doc. That's going to say add employee data. This is really useful if you're trying to create an audit log for stuff that you're putting in. You can run a query. You can see all of the data that you added and also why you added it. You could see an application maybe adding like a application user ID in there or something if you want to track who made this change to the data. And then finally, we put a timestamp on every transaction. So we already talked about this second point here. I don't think I'm going to bring it up again. But the first point, you'll notice in this other slide, like this is way nicer, right? This is way more intuitive to think about and to write in code than this stuff. So the transactor really ought to be able to just take like a regular hash map and turn it into this automatically. It's going to be able to do that at some point, but right now it can't. So you'll see in the demo, we're going to transact things using this syntax.
Or perhaps you need an envelope or something because you have metadata about the transaction you're including as first-class citizens with the primitives as well here, which creates some potential namespace collision. You have to like reserve that name, right? But maybe putting an envelope in there instead, because also you have a retract in the middle of ads. So which is it? You can't do that by just. So you may want to think of an envelope that says, here's how to treat this payload, right?
What I was
a higher level
thinking,
transaction or something.
This is totally not set in stone yet, but I think if you just wrap this thing like in a vector, right? If you just make it a list, then you can intermix maps that represent like your entities with like regular old transaction statements. And I think that basically gets you there, right? Because then if you want to do a retraction or make some assertion about the transaction ID, you just do that as a regular transact statement, but you preserve this kind of convenient syntax. I'm not sure. There's probably some problems with that idea that I haven't thought of.
Is that the only reasonable transformation for that input? Like the only way that you'd want to encode a vector is as a literal Eden vector, but the only way you'd want to encode a map is as a target graph object? Well, or would you sometimes want to, do the other and then use and have a list represented through sub entities and a map as a literal object?
Oh, I see what you mean. So you're talking about in like the value field?
Yeah, I'm sorry, that's right.
I think both are valid. It probably depends on your use case. If you are interested in relationships between entities and making queries on them, you almost certainly want to have each entity have a unique ID.
Yeah.
If it's like, say, I don't know, a shopping cart with line items, and the line items will never exist independently of the shopping cart, that's when it maybe makes sense to just have those kind of embedded as Eden inside the value field.
Sure.
But in your example there, on the left, you have both vector and a map embedded, and your semantics picks one for one meaning and the other for the other meaning. Like, what if they put and are you looking at sets or anything like that, or any other kind of collections?
You could definitely put sets in it. I haven't tried it yet. Probably blows up, right? That's a good point, though. See, this is a perfect example of how I haven't quite thought through what I want the transactor transformation to be.
Right,
yeah,
that's
because
that's what we're here for,
All right, well, we can all think about that when we talk about querying. So this is just a set of facts that I'm going to use as query examples. We're going to do a lot more query examples during the demo. So I think I'm not going to spend a ton of time talking through all of the queries. I just want to kind of demonstrate the capabilities of the system. Let's see, what are some interesting things about this set of facts that we should call out? All right, well, we have references to each other, right? Oh, there's a typo here. This is supposed to be a transaction ID. All right, well, there's some typos in this. We have some values that are maps. We even have values, that are lists. We have values that have lists within lists. And we have one retraction down here. So, clearly at some point someone moved, right? And we took away the address field. So given all of this, oh no, what happened to my arrows? They're weird and big. That's okay. The first caveat, like I said before, there is no client yet. So this is the raw data structures that the database speaks. And presumably the language clients will wrap this in something slightly nicer for whatever language it is. So a query has a minimum of 2 clauses. And in fact, right now it can only have 2 clauses because I haven't done any other ones yet. It's the find clause and the where clause. So the find clause says what you want. And the where clause describes the parameters under which you want those things. Any symbols that start with a question mark are variables. And so variables are kind of where the magic happens. So it's called unifyDB, right? That's named after an operation called unification.
Mhm.
What does unification mean? Unification means that for any given set of facts that are returned from the database, the query engine will guarantee that all variables that are the same are going to refer to the same thing in that set of facts. So in this example, we're saying we want to find a variable called E and a variable called what, where, and now we go into some pattern matching. We have a tuple that looks like E, entity ID. The job attribute is a computer what. And so unifyDB is going to go and it's going to look through all of the facts that it knows about. And it's going to find all tuples that match this pattern. And it's going to unify the concrete values that it finds in those tuples with these variables that you set up. And it's going to return to you a list of all possible unifications that it found. So in this case, we can see that we got unifyDB2 is a computer programmer, unifyDB1 is a computer wizard. And I'm looking at this and I'm realizing this is actually slightly wrong output because we put what in the tail end here. So this really should just be programmer and wizard. So does that make sense? That's the fundamental piece of the query language, and everything else is just kind of built on top of that.
A quick question, Jeremy.
Yeah.
So is this query language identical to Datalog, or a subset of Datalog, or a dialect of it? What I see so far is all Datalog.
Yeah, you could call it a dialect of Datalog. It's certainly, like, if you're talking about like Datomic flavored Datalog, right?
Yeah, well, I mean, it exists independently of Datomic, but
yeah. It's a dialect of Datalog in the same sense that the Datomic query language is a dialect of Datalog.
Got it.
So I don't think like the actual concrete syntax is unique to unifyDB as far as I know. It's pretty similar to other ones, right? Because there's really only so many ways to express the same concepts. But right. You certainly couldn't like run these queries against Datomic and expect to get results that make sense.
Oh, yes. Thanks a lot.
Well, I see you've got a variable nested inside of a Clojure data structure. So that's kind of neat. There's a couple of the, like, I think is DataScript, I think, is another Datalog, Datomic-like Datalog on top, and I don't think either Datomic nor DataScript can do that. So that's kind of an interesting feature.
Thanks. Yeah, I was proud of that one. I've never tested it on anything other than a list. I bet if you give it a map, it would blow up. I should do that. Maybe we'll do it live. It'll be exciting.
That'll be exciting.
All right. So the second query here is slightly more complicated, showing off a few more features. So first of all, you can have multiple where clauses, and they are implicitly anded together. So all of these things must be true in order to unify with the find clause. So what are we asking for here? This query is saying, please find me the salary of everyone who makes less money than Ben. Okay, how's it saying that? So first, we have this pretty generic clause up here. We're just binding the variables E and S to any tuple with a salary predicate. We're saying there's some entity called Ben with a name Ben BitDiddle. And then we're saying there's some value called BS with a salary predicate and the Ben entity. So this gets us Ben's salary. All right, this part's pretty cool. So what's this in here? This is a function call. UnifyDB does function calls. It can only call functions in Clojure.core that are predicates. So anything where you give it arguments and it returns a truthy or a falsy value. So in this case, we're saying if this thing that we bound to S is less than this thing that we bound to BS, that's going to unify. Otherwise, it's not. And then finally, we pull out the name of whatever entity we bound to E. And in our example data set, we end up with just one result.
Do you do any, sorry.
No, go ahead.
Do you do any validation on inputs, right? Like Datomic has a type system, but theoretically, your S and BS variables could be pretty much anything. So is it kind of up to the user to not call functions on values that don't make sense or throw exceptions?
It absolutely is up to the user right now. So this is where that schema system is eventually going to come into play. So the idea, I've been playing with calling it gradually typed database because I think that sounds cool. But the idea is that every value, every predicate in your database starts with this like implicit any type, can be anything you want. But you can transact a schema against that predicate that says this predicate is a string. And from that point forward, any facts you have in your database that are that predicate have to be strings. And then, I imagine on top of that, you could write some sort of like function validation system that says, this function can only be called with these types. But I haven't really thought that through.
But that could be annoying if you're unifying here. So S and BS you could be sourcing them from anywhere, really, in your query. So even if you do type it, you may want to define semantics that would say if these are predicates that there's failure if they don't match. You don't want to like put restriction on where you could use it, but you may define failure semantics that allows still that freedom to use it more freely, but only be true when it makes sense.
Right. Yeah. I think if we're living in this gradually typed world, maybe that's a case where you just say this is an any type, and I don't care what goes in there. All right, let's talk about rules. So this is, if you're familiar with data log, the part of data log where you infer facts from other facts. Right now in UnifyDB, this is something that you pass in through the query. I guess I lied when I said there's only 3 classes. There's only 2 classes. There's actually 3 classes. I think probably eventually rules are going to be persisted into the database because then they take part in the transaction system, and then you can have multiple versions of them, and you can query your database against rules that were true in the past, and there's all sorts of like cool stuff that goes in there. But that's not how it works right now. So what does a rule look like? A rule has, and I'm going to mess up my data log terminology right now, so Michael, feel free to jump in and correct me if I get it wrong. A rule has a head, which is the thing that will be true if the rule's body, which is the rest of the rule, unifies. So this rule says person 1 and person 2 have a lives near relationship if a few things are true. So the few things that are true are also showing off a couple other cool features of UnifyDB. Let's go back and look at our example data real quick. Look at these address rows. So we can see that an address is a list, and the first thing in the list is always the town, and then it has the road, which is a nested list, and then it has the number. And all of our addresses are formatted like that. So if we go back and look at this rule, we can see that we want our address to have a town variable. And we have this weird ampersand thing, and then we have an underscore. What do these mean? Underscore is just a wild card. Underscore says, I don't care what goes here. Anything will unify with an underscore. An ampersand is the rest operator, right? So this is like when you split a list in Clojure, when you're destructuring, you can split it into first and rest. That's what this is doing. So really what we're saying here is take the first thing in this list, that's the value of address, and bind it to town and throw away the rest. We don't care about it. So we're going to pull out the town from person 1. And then we're going to say person 2's address is also that town. Because remember, unification only works if variables with the same name have the same values. And finally, we're going to put another predicate on this, because if we just left it like this, then people would unify with themselves, and you'd end up saying everyone lives near themselves because they all have the same address as themselves. And we say that they're not the same person. But what's the same thing? We didn't have any facts in our database called same. That's another rule. And same is a really simple rule, right? Something is the same if it unifies with itself. So we put all this together, given that example data set, right? We say who lives near entity 1. And we end up with one other person. You don't have to take my word for it. We're going to run this query in the demo. Does this make sense?
So you're doing anything to avoid the combinatorial explosions that you're possibly setting up here?
No.
That's a future. That's a red. Okay.
Yeah, that is. I didn't actually put this in the roadmap, but there will be a query planner, and the role of the query planner is going to be to put the most restrictive where clauses first, right? So, you know, for example, same XX, that terrible clause that's going to unify with literally everything in the entire database. And if you put that one first, then the way the query engine works, it's going to go in, it's going to pull every single fact out of the database, and then it's going to try to unify it against the rest of the query. Person, address, something, that's a much better one, because we only have 3 facts in our database that have the address predicate. So by putting this first, we severely limit the impact of putting same down here.
So are you thinking of using a discrimination network, like a ready network or something like that?
I don't know what that means, but maybe.
For the forward chaining production system languages there's a number of algorithms. A lot of them are based on, the first one was called RETE, R-E-T-E, but it's a discrimination network for basically managing small change in state and very efficient matching. But there's a lot of technology around optimizing that, and also, you know, distributing it over nodes and things like that. It's been around for a couple decades, but that might be a technology underneath you may want to think about.
Yeah, I'm going to go look that up after this. All right, so that's rules. Last thing to talk about querying is time travel, right? Which is a really like stupid and buzzwordy way of saying you can query stuff in the past. So remember, we have these 2 facts. We are asserting someone's address, and then we are retracting it in the next transaction. So this query, again, using this REST syntax, right? We're going to break it up into the first thing in the address, which is going to be the town, and then the whole rest of it is just going to be a list that has the road and the number. And so if we query against transaction ID 2, when this was true, then we get back Cambridge, Mass Ave, 78, right? If we query against transaction ID 3, the exact same query, we end up with nothing, because that fact no longer exists. So this is why it's in blue. I'll show you the API for this in a little bit. It was heavily based on Datomics, and I'm not sure I love it. It involves passing in the transaction ID that you want to query against as kind of like an external like metadata kind of thing against the query. It's not part of the query data itself. And I don't know.
So this is where you could tie a timestamp to your transaction IDs and then use that to translate when someone says, as of like last Tuesday at this time, then you can figure out what transaction level, where you were at in the watermark there, and then use that to, you know, and rather than, because people aren't going to know their transaction IDs, right? They're not going to relate that to time.
Yeah, that's where this gets, like if I were to make transaction IDs millisecond timestamps instead, like then you don't even need to know any transaction IDs. You just say like, I want to query the database as of last Tuesday, and just like magically, we're going to only return things that have a transaction ID equal to or less than that timestamp.
As long as it's the right level of granularity and you're serializing properly, right? So you don't have.
Yeah, I mean we do, and we run into like clock drift and stuff. It gets a little more complicated.
Yeah, right. That's the trouble with timestamps, but.
All right, so that's the time travel piece. We're going to also demo, how you can query your history of transactions and just see everything that's happened. All right, we're almost done with the me talking at the screen portion, I promise. So what is the architecture of this? You'll see that most of this slide is in red. The reason for that is I wanted a fairly abstract and generic system that could plug into a lot of different concrete implementations. And so I wrote pretty much all of the infrastructure components as like Clojure def protocols that callers can implement. And I implemented them to the bare minimum that I needed to like test the system and make it work. So most of the actual deployment infrastructure and stuff isn't there yet. So that being said, this is what unifyDB looks like. So we have the world over here. The world really wants to make queries and store data. The world only ever talks to the web server. And you can see that the web server can be parallelized as much as you want. It's horizontally scalable. The web server uses a message queue to talk to the other two services, which are the query service and the transact service. And so the message queue, again, this is just an interface. Could be like Redis streams or Kafka. Probably going to try to have adapters for the most common ones, right? When you do a query, the web service pops a message in the message queue. The query service receives it and says, oh, I need to do a query. It's going to first go look in its key value store, right? And the key value store, again, this is just an interface. This was probably the trickiest part of this project. So are you familiar, are people here familiar with B trees? Okay, I see some nodding. So just briefly then, a B tree is a data structure. It looks a lot like a map. Sorry, it looks a lot like a binary tree, except nodes have like hundreds of values in them instead of just one or two values. And I'm not going to go into the details because it makes my head spin. But basically, they're like a highly efficient way of looking up a lot of data because you load big nodes into memory and then you do a binary search through them, which is pretty quick. So the B trees that power unifyDB are implemented on top of this generic key value store interface. So each B tree node has a key, and then the value of that key is just like this huge Eden blob. I'm using the Nippy Clojure serialization library, just like compresses it a bit. It's pretty fast to serialize it. So the result of this is unifyDB will run on top of existing key value stores, which is killer because that means I don't have to write a key value store until I'm good and ready. Right now, there's only two. There's the in-memory key value store, which is just a map. And then there's the JDBC implementation. So you can run unifyDB on top of like SQLite or Postgres or whatever you want. Transact service, kind of the opposite of the query service, right? Instead of taking stuff out of the key value store, it puts stuff into the key value store. You'll notice though that the transact service cannot be horizontally scaled. You can only ever run one of these. This is how unifyDB ensures ACID transactions. An ACID transaction is atomic, consistent, immutable, a couple of other things.
And durable.
Yeah, that's the one.
Immediate and durable, right?
Immediate, yeah, that's what it is. Basically,
I think it's isolated.
It's a guarantee
that right?
that if
something like that.
Yeah, isolated. Yeah,
isolated. There it is. Yes, isolated.
I clearly did my research for this. It's a guarantee that if a transaction gets submitted to the database, either the entire transaction is going to go through and your data will be in a consistent state, or something's going to go wrong and none of the transaction will go through. Right, so you're never going to end up in a weird in-between state where half of your transaction went through and half of it didn't. Now, the only way we can guarantee that is by only running one transactor at a time, because otherwise you could receive two transactions at once. They could end up in contention for the key value store and you could write garbage data. I think that there's probably a way to make the transactor horizontally scalable, because if you actually want to run this thing in production, like you're eventually going to end up at a hard limit of how many transactions per second you can do, even though that,
Well,
that limit can be huge.
You can do sharding techniques to help spread the load out by,
yeah,
you know, I mean, there's ways you
gonna
can
have to be something like
get
that.
some parallelization and still keep your acid. Yeah.
Right, but it's complicated, and
Yeah.
I didn't want to deal with it yet. So one transactor it is for now. That being said, I actually think that this architecture like will scale perfectly fine for almost all production workloads, unless you're Google. Like, you know, run the transact service on a really big node in AWS. Like it's the JVM, it's pretty fast. It's probably going to be fine. So one really important note about all this red, I haven't actually implemented any implementations of the cache or the message queue that aren't in memory. So you can only run unifyDB in single node mode right now. It all has to be running in the same JVM, otherwise the services can't talk to each other. But once that's no longer the case, you can run all three of these services as separate programs, and you'll be able to scale at least the query service and the web server horizontally as much as you want. All right, that concludes me talking at slides portion of the evening. Before we go on to the demo, anyone have questions or comments?
I'm kind of curious about the details of the B trees and the way that you're using the key value store, but I'm happy to also leave that question for after the demo, if that would be a better time for it.
Yes, I think that's probably a good question for the diving into the code base portion.
Sounds good.
Because like I would even have to go look at the code and refresh my memory on how it worked. It was like, if you look at the commit graph of this project, it was like I was chugging along, get to the B tree thing, and then it's like 4 months of no progress as I try to figure out how the whole thing works. And then it's a big deal. The day I finally got it working, I was like shouting. My wife thought I was really weird. All right, let's do a demo. Okay, is this text readable to everyone? Cool.
Yep. You make it just a little bit bigger.
Yes. How's that? Good. All right. All right. So I've left some comments here about what I'm doing. I'm just kind of skimming through the setup stuff here, right? So starting the system basically means spinning up those three services we were just looking at, which are all kind of running in memory in the same JVM right now. So we're going to transact some facts. This is just an extended version of that same data set we were looking at earlier. So we can see the use of temporary IDs in here. We're having kind of the same fields that we saw before. We've added a couple more people to it. And then finally at the end here, we've put like a documentation string on this transaction. So we are going to go ahead and transact this. And we can see that we got a whole bunch of stuff back. So every time you transact, unifyDB is going to give you what's called a transaction report. So it tells you the value of the data, the latest value of the database transaction after you did it, right? So we see that we ended up with a database whose latest transaction is 6, ID 6. It's going to show you all of the data that it actually wrote, because remember up here, this is kind of that weird in-between transactor notation. And down here, we've translated it to actual tuples. So this is basically what you would expect all of these things to look like. We've assigned concrete IDs to everything. We've resolved the temporary IDs. So when entities reference each other, those are now resolved to IDs. And the final thing that the transaction report is going to tell you is what the temporary IDs were resolved to, in case you want to do more queries on it or transactions on it afterwards. So this is just a map, mapping those temporary IDs to the things that you made. So that's a transaction. We now have a database that's full of data, so that's great. I wrote a little helper function to query the database because, like I said, there's no client right now, and it's kind of ugly to do a query. So let's look at what this is doing. So it's a multi-arity function, can either just take some query data or it can take some query data and a DB value. And the one arity just kind of delegates to the two arity. A DB value is this kind of weird way that I was telling you about, where you pass metadata to the query engine to tell it which ID, which transaction ID you want to query against. So you just say TXID, either give it an ID or you can just say latest. So I don't care, just whatever the current value of the database is. And then the rest of this is super uninteresting. There's this query function, which is like submitting something to the message queue. We are pulling out the message queue implementation from a global state object that exists just in like the REPL namespace. And finally, we are dereferencing it because this thing is going to return a future, and we are pulling out the results key. So basic pattern matching, right? We can answer questions like, what is Ben's salary? Okay, Ben makes some money. That's cool. I think this is actually identical to the example query we saw in the presentation, so I'm not sure there's much else to explain here. This one's a little more interesting. This is trying to showcase how unifyDB can make sort of graph queries, right? So we want to find back references to people Ben supervises. So entities who have supervisor of Ben. And we want it up to 2 levels deep. So we want to know, who does Ben supervise? And also, who are people that Ben's supervising? So how do we do this? First, we say what we want to find, which is the employee and the supervisor. And we're going to say there's some entity E whose name is employee, and there's some entity S whose name is the supervisor. And then we have some compound queries. So we have an OR, which we haven't seen before, but it works exactly like you'd think it would. Our OR condition is either S directly supervises E, and S is Ben, or S supervises E for some S, and this S's supervisor is Ben, and then Ben is Ben. Something to notice here is we're reusing this variable S in here, but because it's on opposite sides of an OR compound query, those aren't going to unify because you can never have both of them true at the same time. So if we run this, we see, okay, we've got Alyssa, who's supervised by Ben, we've got Lem, who's supervised by Ben, and we've got Lewis, who's supervised by Alyssa, who's supervised by Ben.
Quick question.
Yeah.
So the 2 levels there immediately makes me wonder whether you can do recursive queries and find the supervisor tree all the way down.
You sure
Is that
can,
possible?
but you'd have to use a rule for that. But rules can be recursive. So rules can call themselves. Oh, that would have been good. I didn't put one of those in the demo. Maybe if I'm feeling brave enough, I'll try to write one live, but no promises because I'll probably get it wrong.
That would be gutsy.
But yes, you can definitely do that. You just can't do that without using rules. Okay, so this is kind of the thing that we were talking about earlier, where you can put variables inside your collection type values. So right now we want to find all of the job subtypes of people who do computer stuff. And we do that. We end up, okay, we get Alyssa, Lem, and Ben, 2 programmers and a wizard. Then we do this destructuring thing, right? So this query is asking for all of the addresses in Somerville, well, Slummerville. By the way, all of this example data is pulled from the book Structure and Interpretation of Computer Programs. I would highly recommend, if you haven't read it, it's like mind expanding. Most of unifyDB's query language is pulled directly from chapter 4 of that book with like a couple of modifications to make it slightly more production ready.
That book's been around for a long time.
Yeah, since the 80s. But what's crazy is it's still totally relevant.
Yeah.
It is aged incredibly well. All right. So we're asking for all of the addresses in Slummerville. We execute it. We get 2 back, right? And someone lives in Davis Square and someone lives in Ridge Road. Notice we used a wildcard here because we don't care about the entity. We're only asking about predicates and values here. This is also kind of interesting because it shows how unifyDB can be used as a sort of column store where the predicates are the things that matter and not the entities. I think this is what makes the triple store so powerful. A lot of, there's this book written by the guys behind Neo4j, you know, the big JVM graph database. And they spend a lot of time trashing on graph databases that don't have what they call index-free adjacency, which basically means given a particular node, you have an in-memory data structure that lets you traverse directly to the next node and you don't have to look it up in an index. That's not how unifyDB works. Everything is operating on these B-tree indexes. But if you give up index-free adjacency, you kind of get this really neat flexibility about the types of questions you can ask the database. All right, predicate functions. This one's really basic. It's just asking for everyone who makes more than 40K. Again, this book was written in the 80s. I think that was a lot of money for programmers back then. So we get back these three entities here. This is a slightly more interesting predicate. Like I said, this is anything in Clojure.core with the exception of eval and read, because that would be really bad if you could just put those in your queries. So here we're asking for a regex match, anyone whose first name begins with a capital L, right? We say, okay, it's Lem and Lewis. So this, I think, is totally cheating. It's like completely cheap way of adding interesting predicates to my query language because I didn't write any of them. I'm just letting Rich Hickey do all the hard work. But it worked out pretty well. The question in my mind is like, let's say I write a Python client. What does this query look like if you write it in Python? I have no idea. I want it to feel native, and I've kind of been avoiding that question for a while. All right, Alyssa's gonna move, and now we're gonna look at some of this history stuff. So we're going to retract that she lives in Cambridge, and then we're gonna say she now moves to Boston, moved across the river. And we're gonna put some documentation on this transaction as well. So we do transacted again. Again, we get the CX report. That's a little shorter. And this confirms what we see. The interesting thing here is we now have this retraction fact that has false as its added value. And now we can ask which transactions changed Alyssa's address. So like I said, there's no aggregations right now. This is going to be a lot nicer when you can group by transaction ID, but right now you can't. So you just get back one result for every fact in the transaction, even if they share a transaction ID, right? So we're introducing a new keyword here in your database value. You can ask for historical data. And if you do that, we turn off all of the filtering on transaction ID. And we also turn off all of the filtering on cardinality. So when you ask for historical data, you are always going to get back every fact that unifies with your query, regardless of its transaction, as long as its transaction is less than the transaction value that you ask for. Does that make sense? That was kind of a confusing way to say that.
Does that include retraction facts?
Yes, it does. Yeah, so even if there is an assertion followed by a retraction, you'll get both back. So let's see it. So we make this query, and we see we got 3 results back. I guess let's talk through the query, right? So we're asking for the transaction ID, the address, the added value, and the doc. And we're going to bind some entity to Alyssa. And we're going to say this entity has an address that we bind to our address variable. And remember, these are actually 5 tuples. These are not 3 tuples. So we can just put more stuff to match on in here. So we are also going to match on the transaction ID of this fact and the added value of this fact. And then finally, we're going to pull the doc from the transaction. So when we do that, we can see we get 3 results back. We can see that in transaction ID 7, we retracted Alyssa living in Cambridge. In transaction ID 6, we asserted Alyssa living in Cambridge. And in transaction ID 7, we asserted Alyssa living in Boston. It's going to be a lot nicer when you can group and also when you can sort, because you probably want these back in the order that they were done and not in the somewhat random yet deterministic order that they currently come back in. But this is pretty cool because now we know the transaction values to query on at some fixed point in time. So we can say, at the latest version of the database, Alyssa lives in Boston. But where did Alyssa live at the version of the database in the previous transaction? So here we say our transaction ID is 6, not 7, which we pulled from that query that we made earlier. And if we do this, at transaction ID 6, Alyssa lived in Cambridge. So I feel like there's probably some other like interesting things that we could do with this system that it doesn't do right now. I think what's in place is enough to give you a complete audit trail for everything that happens in your database, which was one of those guiding principles. So I'm probably going to leave it like this until a lot more of the database is done.
So do you have to worry about data integrity across these things? I mean, if you're looking at a history of basically one relation, you know, then it's been serialized, right? So you have this. But what if Alyssa changed her name in the middle of this? Or what if, you know, if you're going across multiple things, you have free variables here. You're not restricting it to be a point in time in that in that watermark where you have a consistent set of relationships that actually happened in the past, right? Or do you?
But you do, because you are always querying the database at a specific point in time. So if we look at this query, it's true that right now, Alyssa's name is Alyssa P. Hacker, but she could change it. However, we could put a concrete transaction ID in this database.
Well, yes, I understand you could do that by setting the watermark, but in the way you're doing it now to query across all these things, you can get a mix of things that would represent state returned to you that never really happened together, right? And that's a danger, right? Because it's like, well, no, that's an individual fact level, right? You will have one discrete value at like on a transaction, but if you're like going across things, they may have been at different times. Like saying like, what color, you know, was your car last year? Well, it was blue, but actually I didn't buy it till this year, but it was blue last year. Someone else owned it, you know, it's, you know, those relationships become also like effective dated kind of content, right? Or date stamped kind of content that you would have to kind of unify across.
I mean, I think that this technique here, where I ask for an entity by name, is probably flawed for the reason that you're talking about, right? The name.
Well, it has limitations. That's all. I mean, because it certainly is. It works well for, you know, for a vertical slice on a narrow thing. But when you start getting relationships in there, then it's a whole nother. You know, you could be misled perhaps if you try and read too much into it. When you make it more complex queries, you got to watch out for that. I don't know. But
entity IDs are fixed. So
yes,
if all you care about is the color of your car, it doesn't matter what the color of the car is. Over the lifetime of the car in your domain model, it's always going to have the same entity ID.
Right. Yeah, they're immutable. Makes sense.
So I think that kind of addresses this. That at least addresses it in that you always have a consistent view of the entities in your domain, like whether or not that view makes sense in your real domain. I think is probably, I don't think you can solve that problem in a general way, right? Like there's nothing stopping someone from transacting a fact that says your car was blue 5 years before you owned it.
Right.
All right, I only have one example left. This is showing rules, and I was not feeling creative by the time I got to this point in the demo. So this is the exact same thing that we saw earlier. So we'll just talk through it like really briefly, because we already saw it. So we're binding some Ben entity whose name is Ben BitDiddle. And we're saying we want to know who lives near Ben. But lives near is not a fact that's in our database. So we're going to need to tell unifyDB, how can we infer the lives near relationship? And then finally, we're just going to pull the name from this who variable. So we have a nice result. So lives near, person one, person two. We declare our subject or our head. And this is the thing that's going to be true if the body unifies, right? And then remember, we're going to unify across the two same town variables, but on two separate person variables. And we're just going to throw away the rest of the address field because we don't care about it. And it can't be the same person. And same is defined as something that unifies with itself. So given all of this stuff, we run this query. Only one person who lives in the same town as Ben, Louis Reasoner. And go back up and look at our facts. We can confirm that out of all of these, only Ben here and Louis here live in Slumberville. That is all I have for the demo and the presentation. It's 8 o'clock now, so I don't know, Elena and Mark, what do we want to do for like a Q&A or code deep dive, or? But I'm flexible with how we go from here.
Yeah, me too. Yeah, we can, if you have any wrap up, you can do that. Otherwise, we can move right into a more extensive Q&A or deep dive. And for those of us who need to go and have dinner or attend to other things, might be a good time. And we can maybe just take a couple of minutes for that, and then.
All right, are we live?
Yes, we are.
Okay. All right, I'm gonna start with the questions that were in chat because we had a bunch of them come in. And then after we get through all of those, if there's still time, we'll take more if people have any. Okay, so first up, have I thought about putting a gremlin or a Cypher query language on top of this? I have, and I kind of rejected the idea for the reasons I talked about at the beginning, which is that I think that text-based query languages lend themselves to misuse in a way that a data structure-based query language simply eliminates. Like, I really like the way that, is Cypher the one that Neo4j uses?
Yeah, yeah, although they've open sourced it, but Gremlin is functional, so that may be more like aligned to the to the environment that you're thinking, or the idioms.
Yeah, I like the idea that the queries kind of visually like represent the relationship between the entities. That's really cool. But I don't have any plans to do that for unifyDB. Yeah. Thoughts on the visualization of my graph? I do have thoughts on that. I think what I would like to do is write kind of a UI service that would be an independent project from unifyDB that just uses the unifyDB API. And it would let you visualize the graph. It would probably let you run queries, make transactions, like again, in the spirit of like things that should just be built into the database that developers don't have to build. Like every dev at some point has been asked to build some sort of like backend system for like service team members to look at the database, right? That's incredibly common. So I would love to have a UI that is that you just get for free.
Sometimes it's easier to handle than just like tables of tuples, right? Yeah, to actually see the information better. Yeah.
And you could even see like, maybe people will be more comfortable with a spreadsheet format. You could translate those tuples into a spreadsheet. You just have to determine which predicates go on which axes.
Yeah.
All right, there have been a couple of other Datomic-like open source DBs. Did I learn from them or consciously avoid them? I wouldn't say I consciously avoided them, but I certainly avoided them. I think this project started as basically like Datomic's really cool, but there's stuff I hate about it. How can I fix it? But it pretty quickly evolved to like, databases are cool, but there's stuff I hate about them. How can I fix them? And I moved away from that influence. And I haven't really like looked, I would say the closest influence I've had other than Datomic is Neo4j. And that is really more like a conceptual influence, but my implementation has basically nothing to do with the Neo4j implementation.
Oh, great, thanks.
Our rule, yeah, of course. So are rules stored on the DB, and can one change a rule? Not right now. I would like them to be. I think that makes more sense. Right now, you pass a rule in the query, which is, it's really flexible, right? Because you can have a fresh set of rules for every query, but you lose the ability to have like a sane rule management story, you know, like where are you just gonna have like a giant code file with all of your rules that all your queries pull in? Like, I don't know. So I think that rules should be stored in the database, but they're not right now. I do not like green eggs and ham. Do you guys ever do the green eggs and ham thing? Like in preschool, the food color that released, it freaked me out. Just felt like food shouldn't be that color. The most fun part of the database to implement so far, I think it depends what you mean by fun. Like the B tree implementation was the most satisfying to get right. That felt really good, but I really hated writing it. Like it sucked in the moment. I think the query engine was really fun because it like the query engine is this like really elegant recursive pattern matching implementation that I didn't come up with it. I pulled it from structure and interpretation of computer programs. But it's just like kind of like deeply satisfying and beautiful to see it all run. And like it feels like most of structure and interpretation of computer programs, like they've given you these small building blocks. You know, this is how you unify a single query. This is how you construct a compound query. And they come together into something that lets you write like crazy and wild and complicated questions that don't seem like they should be possible from those building blocks. All right, would a retracted fact that never existed show up in a transaction history search? It definitely would. That's just going to show you any fact that's ever been transacted. I don't know if it would make sense to have the database reject retractions that have never been asserted. That sort of feels like it would be an artificial limit. I don't know if there's any valid use case for having
there's a reason
that,
why
there's
you
reason
why you might want to keep that, and that is, or you may want to allow this, is because if you're like doing like event sourcing, or if you are, or you're coming in the middle of a stream, if you don't allow that, then you have to like artificially find some starting point, or go back to the beginning of time when the initial things were birthed. But you could like dip your cup into the stream knowing that you're going to get some retractions from things you didn't even know were facts, right? But it will self-correct, you know, over a little bit of time, right? So that may be a use case for keeping what you have the way you have it, allowing that situation to occur. It may increase the utility of this in like tapping into a stream of changes from an event source. But
yeah, that's super interesting. That makes a lot of sense, right? Because if you are event sourcing and you come in the middle, like you get an event that says like Alyssa moved, and you're like, who's Alyssa?
Alyssa
like,
could have been in there a long time,
right?
And you have to go way back in time to get where she was initially created, and then there's something was in an existing state before that. You'd have to go to the beginning of time, which may not be practical or available.
Well, there you have it. Retractions without assertions are valid, and they're here to stay. What have I learned that I think can be applied to other projects? That's interesting. I mean, this is kind of a boring answer, but I've gotten a lot better at writing Clojure since I started this project.
No, that's a great answer. Like what? In what ways?
Like the value of the core.match library. It's incredible. I was kind of not super exposed to it before this, but the nature of writing a database is that you need to do a lot of parsing of various sorts. And like, it's just this incredibly succinct way to like chomp up a data structure and pull out exactly the pieces you need and nothing else. And you end up with like code that is both succinct and readable, which is the holy grail, right? I think that the B-tree part of this project was the first time since college anyway, that like I've been seriously exposed to like, you know, a computer science-y data structure that's not just a hash map. That was really valuable. Like when else do you get to implement a data structure from scratch, right?
Right. Did you see any similarities between B trees and the Clojure internal hash tries?
I don't know too much. Actually, I actually don't know too much about the persistent data structure implementation.
Okay, no, that's fine. That's fine. I was just curious. It's okay.
I actually think they're actually quite related. You know, they have a kind of a similar thing about, you know, the core node, you know, the maximum value set in a node and how it splits is different, but it's but the idea of doing that is very similar.
That's interesting. That makes me feel like I should be like, I don't know, persisting raw data structures into the B tree somehow.
B trees are real common underneath a lot of databases today. A lot of your relational databases are built on B trees. Yeah.
Mm-hmm.
All of your indexes are B trees for sure.
Also, all of the B tree content on the internet is shockingly bad. It's all just like someone's notes on their like CS 101 course.
Right.
And I ended up like buying a, this is when my wife thought I totally lost my mind. I ended up buying a paper that someone, like some database engineer had written about B trees. And I would like read it before bed. And she was like, "What are you doing?" And I was like, "I'm reading about B trees." And she just like kind of gave me this look. But yeah, that was definitely a learning curve. I'm glad I did it.
It won't help you probably with implementing B trees, but the book, Martin Kleppmann's book, Designing Data Intensive Applications, has some really nice stuff about how they're used in databases. Actually, the book, you might, it seems like you're pretty into databases now, you might really enjoy the book. I thought it was a fantastic read.
Yeah, we're doing a book club with that in my company. A bunch of engineers are reading that chapter by chapter and chewing on it. It's really good. Yeah.
That's awesome. What was the author?
Martin Kleppmann.
Martin Kleppmann. All right, I know what I'm doing next.
That is a hugely popular book. That's a bestseller in the data engineer world. Say, speaking of pattern matching and so on, you know, there's core logic, and that does a form of unification. And I really don't have a sense of whether it's the same sort of unification that happens in these database queries. Did you look at that? Is it at all relevant?
Michael, are you still on this call?
Yeah. Did I drop off?
No, Michael. This is his wheelhouse. I'm gonna defer to you here because I don't know a whole lot about core logic.
So
for context, Michael studies this. This is his PhD.
Not my PhD, my previous PhD topic.
Okay.
I have since changed the macro system related thing. But so core logic is kind of Prolog-ish. So the concept of unification is the same, but it's not primarily about doing something with a database. So a lot of the implementation aspects that you would consider, you know, around sort of optimizing a query or something like that are going to be very different. I'm not sure there would be any value in sort of using implementation from core logic necessarily, maybe in some of the rules, but then again, I think in the rule part, you know, you might ultimately end up doing something more like a data log style bottom-up evaluation strategy instead of Prolog style top-down. I don't know what you're doing now.
I also don't know what I'm doing now. Is it accurate to say that core logic, like the whole thing, is kind of fact inference as opposed to starting from a known set of facts and then?
Right. right? You you have rules and you have a goal that you're trying to find out whether is true. And so, if you're trying to find out whether it's true, you find the right thing that matches the head, and you look at each of the ands, the conjuncts, and check those, right? So that's top down. Whereas if you have a set of facts and you derive their consequences, right?
This is the backward chaining versus forward chaining rule system conversation, right?
Yep. So core logic is backward chaining.
Yeah, right. And in your example, in what you have, Jeremy, you could use either or combination in your rules, because if you think about it, if you use your rules to generate new facts and then maintain those and retract when things are retracted and add when things are added, that's like a forward chaining rule system. Then it's available to you. Those facts are already there, versus like trying to execute it or match it or do backward chaining at the time of the query execution. And if you have lots of query executions, the forward chaining may buy you some performance because you won't have to redo things.
Yeah, no, that's really interesting, especially if you pair that with the transactional model where you always have like a consistent slice of data. You could literally just run the rule once, cache those results forever.
Yeah,
which is another argument that rules should live in the database.
I put in the chat a link to Clara rules, which is a Clojure implementation of a forward chaining rule system, which I think they use Reedy underneath the table there for that. I mean, it's pretty common way to do that, but it'd be interesting to think about if you were to put Clara in your server side, so that when you got those rules, especially if you can manipulate them, you could turn around and execute them as Clara rules, which, and then the Clara system would maintain the generation of additional facts along the way.
I really like their
expand
Java
your data
API.
set, your tuples. Yeah, it's pretty slick, but that might be something to think about.
I'm gonna have to come look into this, because this is also a really nice example of having like kind of an Eden native data structure that also feels native in the client language. That's cool.
So I haven't used core match before. I'm curious if there's like a particular part of your code base that illustrates, the value that you see in that. I would love to see that.
Yeah, absolutely. Let's look at the unification logic. Oops. Problem with calling a file in the unifyDB project unify.clj is you have to do a lot of typing to get to it. Okay. So this is kind of like the core function, right? The job of this function is given two patterns, pattern 1 and pattern 2, and a frame. And a frame is just a set of variable bindings. So like, let's say you are halfway through executing a query and you've already bound some of your variables to concrete values. Those are going to be in the frame. And one query can have many frames because there's many possible unifying solutions to it. So the goal of this function, you know what? This isn't using core match, is it? This is just a big con. Huh. Well, that was my ace in the hole. This was like the big one, but this is just a con. I still think it's a cool function to look at.
Yeah, I mean, I'm happy to have you kind of talk us through it. This is also outside of my area of expertise, and I'm always happy to learn.
Let's see. Okay, this is a slightly better example, but it's less important. So this is a function that is used to determine, it's used to sort the facts based on their transaction IDs so that we can eliminate facts that have been retracted after they've been asserted. And so basically, the goal of this is to call a compare such that a retracted fact will be sorted higher than an asserted fact. So if you have two facts that are otherwise identical, the only thing that's different about them is they have a false at the end instead of a true at the end, then the one with a false at the end should come first, right? And so here we have this match statement, and we're just matching on the two facts, or on the two things that we're comparing. And so if the two things are Booleans, we're going to say false has a greater priority than true. Conversely, true has a greater priority than false. And this is where core match gets kind of interesting. You can have like predicate clauses using this like weird arrow note syntax. So this is saying if we call is it a collection, and that evaluates to true on F1, and we call and that evaluates to true on F2, then basically we're going to recurse. This has nothing to do with core match at this point, but essentially, we break down the first thing and the second thing into a first and a rest. We compare the firsts, and if the firsts compare equal to each other, then we're going to recurse into the rests until eventually you get to a base case that is one of the other match clauses. And then finally, if you put like a symbol in a match, it just evaluates to itself and it always matches. So this is the fallback, right? This could be any symbol. It doesn't have to be else. Else is just kind of a nice clear way of saying this is what happens if nothing else happens. Otherwise, we just call compare on them if they're the same type. Otherwise, we get their hashes because we just need to return like some value and we don't care what order they sort in.
Sorry, go ahead, Mark.
I was just going to say, so match must be some big macro because I've never seen those operators before. Colon,
yep.
Bracket.
Yeah, it sure is. It's a big macro with like a ton of different parameters. I mean, I think it ends up fairly readable though. You can do some really sophisticated things within the match clauses. There's also like guards where like you can say this if this thing matches, but then like you can discard the match if some other predicate is not met. I wonder where else I use this.
Sounds like worth digging into. So sorry, Chris, I stepped on your question.
I just had a silly question. I was curious if this was the arbitrary deterministic ordering that you mentioned earlier when we had the like historical query that returned those.
Yep, that's it. Yeah, I mean, ideally, I think aggregate and sort filters in the find clause are high on my priority list because I don't think you can have a proper query language without this. While I'm sharing my screen here, is there any other part of the code base that I mentioned that people would be interested in looking at?
Another nice little example of using match is in Transact CLJ. Oh, you already have that. Oh, you're looking right at it. Never mind. This is the one you're looking at right there. Yeah.
Yeah.
I'm sorry. Did you already talk about that?
No, I didn't. I opened it, but then the conversation moved on. We can talk about it real quick.
Oh, okay.
Yeah.
Yeah. This is one because it's. Go ahead. You got it.
This is the bit that takes those weird transact forms and turns them into facts. But yeah, this is actually a nice use of core match because you can see we're binding multiple variables and also an arbitrary keyword. So like this clause here is going to match any vector that has 4 items where the first item is unifyDB add, and then it's going to bind the variables E, A, and V to whatever the second, third, and fourth items are. And then in this case, we're just going to return a vector that says EAV, transaction temporary ID, and true, because we added this statement. The same thing for false.
Yeah, that is really nice. It's super readable.
Yeah, I think one of the goals, like I haven't done a lot with match, but I've watched some of the talks about it, and I think one of the goals is that the macro produces code that's pretty close to the tightest you were going to do if you're going to do it yourself. So I can't speak for whether it succeeds at that, but having that as a goal means that hopefully you can use it without worry that you should have written it in a more efficient and less readable way, right? So that's neat. I
You
think
heard it
that's a
here
very
first.
nice one right there.
UnifyDB, super fast, really efficient because we use core match.
Nice. Okay, well, I got to run, but thank you very much, everyone, for allowing me to drop in on your, your meeting, and thanks, Jeremy, for being brave enough to show off your system in your code.
Yeah, thank you. It was awesome
I enjoyed
having
it.
you here.
Thank you.
Come back.
Agree.
Yeah. Bye, everybody.
Bye-bye.
All right.
Yep.
Yep. So why don't we make that the end of the organized part of the presentation? We can stop the recording.